Good morning, good afternoon, everyone, and welcome to the HI Weekly Research Seminar. My name is Kurt Langlotz. I'm a professor of radiology and biomedical informatics at Stanford and the faculty director of the Center for Artificial Intelligence in Medicine and Imaging, which we call the AMI Center. I'm also faculty associate director at Stanford HI. I am thrilled to introduce my colleague, Akshay Chaudhari. Akshay is one of our accomplished faculty members in the School of Medicine. He trained here, and we were delighted to retain him as an assistant professor in the Integrative Biomedical Imaging Informatics Division in the Department of Radiology. He's also associate director for research and education at the Stanford AMI Center and a faculty affiliate at HI. In his talk today, Akshay will describe how physics-guided AI is currently being used to improve the speed of magnetic resonance imaging, or MRI, and how we can avoid the large data sets that are required for supervised model training using novel unsupervised and semi-supervised approaches to accelerate MRI. He'll also describe the public release of a 1.5 terabyte data set to help improve MRI images using clinically relevant metrics. Before we begin the presentation, a few logistic details. We will be using the Slido platform to capture your questions. If you would like to ask a question, you can use the QR code on the screen, or you can click the link that has been in the chat and will again be in the chat shortly. You can do that at any time during the presentation, and I'll be drawing questions from Slido after the presentation. So Akshay, thank you again for joining us, and feel free to share your screen and take it away.
Kurt, thank you so much for that very kind introduction, and thank you to Stanford HI for this invitation to present. Hopefully you can see my slides.
Yes, we can.
Wonderful. So I'm excited to be here today to talk about some of the research that my group has been performing on trying to use machine learning to improve radiology. But hopefully over the next 40 minutes or so, I can try to deliver slightly different insights that one might be familiar with. Typically, when we think of radiology and machine learning, we think of how can we teach machines to interpret images? How can we teach computers to be able to classify or segment some of the images that we deal with? However, in my talk, I'll really be focusing on how do we actually build those images in the first place? Can we actually use machine learning methods to significantly improve how quickly we can acquire this data? And I'll guide you through some of the physics that are involved in that and how we're really trying to combine what we know about physics and what we know about machine learning to really drive the best outcomes for our patients. So here are some disclosures. I received some research support, have some consulting interests, and some ownership interests also. So I really wanted to start at a high level and just talk about what is magnetic resonance imaging and why we should care about this in the first place. And magnetic resonance imaging, or MRI, is one of the most widely used volumetric imaging modalities in healthcare. It provides excellent tissue contrast, so we can really visualize a whole host of tissues in any given anatomy. And it's widely used clinically, and it's widely used for research studies. A lot of common applications of MRI include neuroimaging, where we want to be able to better understand the brain structure. And there's a lot of large research trials that are trying to use MRI to better understand diseases like Alzheimer's and Parkinson's. Within musculoskeletal imaging, MRI is also used very commonly because it provides exquisite tissue contrast to be able to differentiate between different tissues within the joints. For example, if one might go skiing and one happens to injure their knee while skiing, probably MRI will be the way that you're diagnosed with any sort of specific injuries that you may have. More recently, MRI has been used for cardiac imaging, where not only can we acquire static images of the heart, but we can also acquire dynamic images to really see how the heart is beating over time, how blood is actually being ejected from the heart, and to be able to get a lot of qualitative as well as quantitative metrics about overall performance. And lastly, MRI, but not definitely the least, MRI is very commonly used in oncology also. For example, it's used commonly for breast cancer imaging, it's used for prostate cancer imaging in order to diagnose tumors, and to be able to assess whether therapies are working and to be able to intervene and change treatment outcomes for patients. So there's a whole host of applications that MRI really has. And I apologize for a little bit of a busy slide here, But I just wanted to come up with one specific highlight. And what we're seeing here is a graph of the number of MRI scans that are performed per 1,000 individuals in any given country. And if we really zoom in to the United States, we'll roughly see that every year, there's around 27 million MR scans performed. And this is only for clinical purposes only. And we can't really track how many research scans there are in the US. So really what I want to drive home here is that MRI is very widely used, but there's also some downsides to how we use MRI currently. And probably one of these biggest downsides is the time that it takes to acquire these images in the first place. For example, an average MR protocol might take anywhere from 30 minutes to 60 minutes of time in this narrow MRI scanner. And what this really translates to is that it can increase wait times for patients. So for example, if someone's physician might prescribe a specific MR scan, it might take 2 weeks, 3 weeks, or even 4 weeks or higher to actually get that imaging test performed in the first place. So there might be some constraints on whether or not we can get timely diagnoses. And at the end of the day, from a hospital's perspective, if we can increase capacity from instead of scanning 10 patients per day, even if we can scan 15 patients per day because our imaging scans are now faster, we're just able to deliver better value care for patients and really try to decrease the overall costs of healthcare, which are already burgeoning within the United States. So that will really be the focus of my talk about how can we increase the speed and the efficiency of MRI. And before we get there, I just really wanted to describe at a high level what that image acquisition and what that data flow pipeline really looks like, because in order to be able to affect change, we really need to understand the full system that we're working with. And for any given image modality, the first step that happens is there's some acquisition of raw data. And once we acquire this raw data, we have some reconstruction methods where we can transform this raw data into the images that we care about. And I will point out that typically, if we want to perform magnetic resonance imaging or computed tomography or any sort of medical imaging, essentially, we seldom acquire the images in their actual form. Not like a camera where we can actually capture the RGB pixels directly. We actually have to acquire data in a slightly different domain and then reconstruct it to the images that we care about. And then lastly, once we generate these images, we can either have radiologists analyze these, we can pick our favorite machine learning algorithms to classify, segment these images. And roughly, anything that happens before the generation of the image, which is the acquisition and the reconstruction phase, we typically refer to as upstream AI. And everything that happens once you have an image already and you're trying to analyze the image, we tend to refer to as downstream AI. And the focus of this talk will really be some of these upstream approaches about how do we build that MR image in the most efficient manner using machine learning approaches. So let's dive a little bit more into what makes up an image in MRI in the first place. Say I want to come up with this image of the brain. Well, the raw data that I actually have to acquire for this is known as the K-space. And what this simply is, it's a Fourier transform of this particular image. And what a Fourier transform is, it's an analytical function which can take any signal and break it down into a whole host of sine and cosine waves with different frequencies and different amplitudes, so that once we add all of these sine and cosine waves, we get exactly the signal that we care about. In this case, our signal is two-dimensional because it's an image. And what this K-space represents is it's a whole host of spatial frequencies. So the center of this K-space corresponds to a point in 0, 0, which just means that there's no spatially varying frequency, so just a flat image. And as we acquire more and more K-space data, we're getting higher and higher frequency information about this image. And what that translates to is we get sharper and sharper images. So if we start working with this K-space information, if we have to sample more of K-space at any given time, so if we're straying away from the center, what does that actually translate to? Well, the first thing that we'll get is, since we're sampling more information about the image, we get more resolution about the image in the first place. So we can now make out more subtle details, or maybe look at very small changes in abnormalities, because we've simply acquired more data. However, the downside to this is, because of the MR physics at play, the noise in all of our images remains the same. And when we acquire more and more resolution, the overall signal that we have in MRI remains constant, but the size of our pixels is actually decreasing. As a result of this, because our noise is constant, our signal to noise ratio actually decreases as our resolution increases. So that's one of the downsides of sampling more case space. And probably the biggest downside that we have is if we sample more case space, we have to spend more time sampling more case space. So this just extends how long our scans actually are. So these are some of the consequences of just working with this notion of the Fourier transform space, or what we call the case space. And here's just a graphical representation of what this looks like. On the left here, we have case space, and we're just showing you what the reconstructions of that image look like at different amounts of varying spatial frequencies. So as we just start sampling this case space, we'll see a very coarse or low resolution image. And over time, as we sample more and more case space, we'll see sharper details being resolved. And if we actually zoom in to this heart right here, we can actually see where this arrow is pointing. There's small artifacts that are slowly being resolved over time. So hopefully some of the takeaways from this slide are that even if we simply sample the center of case space, there's a lot of energy in that signal. So we can build a coarse outline of what we want to image, but to really get that fine level of detail, which is necessary for making clinical diagnoses, we really have to acquire more information. And as I mentioned in the previous slide, if we want to acquire more information to remove some of these artifacts, then we're going to have to spend the time in sampling all of that additional data. So really combine all of these together, I think there's some fundamental constraints that we have based on our MRI scanners. And I like to refer to this as the triangle of fate that you can never really move away from. On one hand, you have a signal to noise ratio, which is how noisy is your image? What can you actually read through? For example, in this particular image, if there's a small abnormality, because the image is so noisy, maybe you won't be able to see it. But if there's a larger abnormality, maybe you'll be able to see it. So it really depends on the use case, what signal to noise ratio is okay. Similarly, we also have to contend with resolution. For some diagnoses, having a low resolution scan might be entirely fine. However, for some use cases, you probably need all that additional resolution because you're looking for the smallest changes. And the last constraint that we face here is, as I've mentioned, scan time. And in an ideal world, if we talk to most of our radiologists, what they want is the scans with the best signal to noise ratio, with the best resolution, but the least amount of scan time, which is always challenging to be able to optimize jointly. Whenever we improve one of these, we necessarily have to degrade the one of the other two. So we basically just have to exist within different operating points in this triangle, depending on what our end clinical goal is. And hopefully over some of the next few slides, I'll talk about how one could potentially maintain signal to noise ratio and improve resolution by keeping scan time constant using some advances in machine learning. And this is really the premise of the overall talk is, can we speed up MRI? And if we just look through what the overall data acquisition process looks like in MRI, if I have a real image, I need to be able to sample that full extent of case space. And once I do that, I can reconstruct the image that I care about. But now, if I'm running short of time in the MR scanner, I could just say, hey, instead of sampling this full case space, I'll just pick some sort of undersampling trajectory where I only sample some limited percentage of the points. So I only end up with a finite amount of data instead of the fully sampled case space. And if I just simply reconstruct these images naively, I can simply put in zeros where I skipped sampling those points. I'll end up with an image that's quite degraded. And if we show this to radiologists, it really does not have too much diagnostic information that it's conveying. So at the end of the day, the name of the game is how much can you undersample your case space while still maintaining image quality and while still being able to produce images that can help with clinical diagnoses and what can add to clinical insights. So it's really this optimization process of getting the least amount of data, but still building the best images from these undersampled data sets. And just from a terminology standpoint, because we know some of the physics that are at play in MRI, we know how an object is represented in the Fourier transform space because we understand the Fourier transform, we understand how the MRI scanner influences that signal. We know what that forward model of the data of the signal itself looks like. And once we have some sort of undersample case space, we know how to be able to transform that into some sort of images at the end of the day. And this is this inverse problem for the given forward model. So just two terms that we should be aware of for the rest of the talk. So some of the first approaches that we took in order to improve the MR signal use this notion of MRI super-resolution. And super-resolution has been around in the computer vision community for the last 2 or 3 decades. But given some of the advances in representation learning, in machine learning, we've been really able to use this in a wider realm of applications. And the premise here is actually quite straightforward. If we have a low resolution image, given priors for the image that I know already, can I actually transform that image to have a slightly higher resolution? And we just wanted to try this in the case of MR scans. And here's an example. So this was a knee MRI scan, which took 5 minutes to acquire. And on the left here, I'm pointing to a tissue that's known as the medial collateral ligament. It's this thin black band, which is depicted by the arrow. And it's actually really hard to make heads or tails out of this, just because there's not enough resolution to be able to visualize that tissue perfectly. What we did was we built a super resolution algorithm to take these images as an input and to be able to improve image quality over time. And passing the same image into a super resolution network, we can see how that tissue is now depicted much better. And this sort of resolution is what is required to be able to diagnose any sort of injuries one might have to the medial collateral ligament or additional tissues within the joint space. So we pass in a low resolution input and we get a higher resolution output as a result. And if we actually compare this to a ground truth acquisition that took twice as long, we see that the image quality is somewhat comparable to the ground truth image. It's not identical, but by spending half the time to acquire the data, we're almost there. So I think there's a lot of potential to use some of these methods to improve diagnostic image quality. And that's exactly what some of our initial impressions were here. By using some data-driven techniques, we actually were able to improve image quality of MR images, which was a very promising first step. But then at the same time, it still brought up quite a few questions. First of all, since this is an entirely data-driven technique, how do we make sure that we're not hallucinating features? How are we making sure that we're not adding additional information into these scans, or we're not removing information that should be there in the first place? Because there's no constraints that these super resolution models can actually enforce during the inference process. And at the same time, this was a supervised learning method. So we required a whole host of images. We used around 20,000 slices of NEMR scans that were acquired over 125 different patients. And that might seem tractable for some use cases. For some use cases, it might be impossible to collect data at that scale at a high enough resolution to train our methods. So there's always a motivation to reduce the extent of training data that we need to solve these problems. And that's where the domain knowledge really comes in, because instead of solving this problem entirely in a data-driven manner, why can't we combine some of our knowledge of the underlying physics? We've been working with MRI scanners for the last 20, 30, 40, 30 years or so. So can we have schemes where we embed knowledge of the physics as well as using the benefits of data-driven systems? And this is exactly what we set out to do. And without going into too much detail, we can actually take into account some of the characteristics of the received signal. We can have different calibration scans that are inputted into the network. And we use what's known as a proximal gradient unrolled convex optimization. And it's a bit of a mouthful, but I'll try to explain what that does. First of all, we can actually cast image reconstruction, the inverse problem that we have, into a classical optimization problem. And there's a whole host of algorithms that we know already exist to be able to solve that inverse problem. And we just represent those as models that we can use deep learning for. And all these unrolled algorithms have two parts to them. The first one, which is known as this DC, or data consistency block, all that does is it makes sure the output of your neural network is actually consistent with the undersampled data that you acquired in the first place. In this manner, by making sure that there's nothing extra or nothing that shouldn't be there in your output image, we're making sure that we don't actually end up hallucinating features that shouldn't exist in the images. And after each data consistency block, we have these CNN layers that can actually improve the image quality. So over time, by stacking these data consistency and CNN blocks in an unrolled and iterative manner, we can start off with our best guess of the image and then convert them into a high quality output at the end of the day. And one of the benefits of this is, since now we've reduced how ill-posed this problem is by injecting some physics and injecting more constraints into our optimization, we can reduce how much data that we need. So here's an example of accelerating scans by a factor of 8. So we're only sampling around 12.5% of the original data. If we naively reconstruct those images by plugging in zeros where we didn't sample the information, we get pretty bad looking images. However, with the same initialization in this unrolled model that I described in the previous slide, we can see that our 3D deep learning algorithm can reconstruct images with a very high fidelity. And if we compare that to a reference image, which is fully sampled, we can see that they're nearly identical. And this only took 10 examples for training. And instead of just solving this as a data-driven super resolution problem, since we now injected prior knowledge, since we injected additional inductive bias into this problem, we can really reduce how much data is required. However, this is still a fully supervised technique. So we wanted to ask ourselves, well, can we think of what is the exact opposite scenario where we may have no training data at all? And this might be reasonable in certain situations. For example, in high resolution cardiac imaging, where we want to be able to image a beating heart, we're taking the same image at multiple time frames, and we want to be able to increase the spatial resolution, and we want to be able to increase the temporal resolution. In these scenarios, we'll never actually have time to acquire the fully sampled data sets in the first place, which would render using supervised methods a little bit challenging because we have no signal to supervise against. Another example could be dynamic contrast enhanced imaging. And this is where we want to be able to image whole 3D volumes of the entire anatomy over multiple different time points. It's commonly used when we inject a contrast agent within the body, and we want to see how this contrast agent is actually diffusing and perfusing in different parts of your anatomy. This is a very high dimensional scan. It requires a lot of data, and there is no way that we can ever get a data set that will be fully sampled, because to do that would require over an hour of scan time. And if we wait that long, all of the contrast injection dynamics that we care about, it'll be too late to capture those. So there's definitely some scenarios where there's just no training data that we have. So we really wanted to test how far we can go in our data limited regime. And to do so here, we were inspired by a paper that came out 2 or 3 years ago called Deep Image Prior. And what that really showed was the structure of a convolutional neural network can actually act as a strong prior for images. So let me explain this graphically and what that means. And I'll have my friend Bill Murray here to help guide some of these examples. So let's just say we start off with an original image of Bill. And then we can transform this by adding a little bit of noise on top of it. The statistics of the noise don't really matter too much. We're simply corrupting the image to some extent. Next, we have the same original image, but now we're randomly shuffling the locations of those pixels. And at the same time, we can also simulate noise with similar statistics as the shuffled image. So now that we have these 4 images, all that I'm trying to do is I'm trying to build a convolutional neural network to be able to simply recover this image after a random initialization. This network has been initialized for the first time randomly. It has never seen any training data in the past. It's a completely untrained network. So I simply want to be able to see whether a neural network can recover a signal that I care about. And we'll see in terms of images, the y-axis is the mean square error. We'll see that the original image can be recovered very quickly in around 100 iterations. We see that the loss in what the image is, what the network is outputting and what the original image is very low. And what that means is we're able to fit to the signal quite well. We're able to fit to the noisy signal quite well, but perhaps not as well as the original image because the noise is random. We can't really predict noise. So it's really hard to take any system to be able to fit to the noise. However, both these images were something that the neural network could rapidly learn to recover. At the same time, this random shuffled image and this image of noise did not have any structure to it at all. And because it did not have any structure, our network really struggled for a long time, around 500 or so epochs, to be able to recover this. And only then did it start overfitting. So we can see that if we're only looking at the first few iterations of the network, because of the structure that exists within the image, we can actually use a neural network to be able to recover that signal. And I think this was a really interesting insight that CNNs can actually fit better to natural images than they can fit to noise. And this was exactly the observation that we used to build some networks for image reconstruction. So here, we started off with the signal of pure noise, and we wanted to end with a knee MR image. And what we used was a very simple convolutional decoder network that we call ConvDecoder. And this is made up of very simplistic convolutional layers. We have upsampling blocks, we have convolutional blocks, we have our activation functions, and so on. And in a completely untrained manner, we can actually force this network to recover the signal that we care about without using any sort of training data at all, because of the observation that this network acts as a prior as to what images it can create. And this network cannot really fit the noise. It can really fit the structure really well. And because our image has some plausible structure, we're able to recover that signal with high fidelity. And this was some nice work led by one of our PhD students, Dave, where we compared the reconstructions of the ConvDecoder to supervised reconstructions. And this was for fourfold undersampling. So on the right here, we see the baseline supervised recons. In the middle, we see our ConvDecoder reconstructions. And on the left, we see the ground truth images. And all of them look nearly identical, except the ConvDecoder method did not utilize any sort of training data at all. So this was really exciting. And we're really exploring where this method works, where this method fails. And it'll be really interesting if this can serve as a basis to reduce some of the constraints of training data. So we talked about supervised examples. We talked about fully unsupervised examples. The next premise that I wanted to talk about is, what if you're somewhere in the middle? What if you have some supervised data where you have labels? And what if you have some unsupervised data where you don't have the labels, which I think could be a very practical scenario. Perhaps one could acquire data from a clinical scanner that has had the luxury to get the fully sampled training data, but now we're deploying this to a different site where we may not have that luxury to get all the training data. So here, we turn to some semi-supervised learning methods. And one in particular that we're using is this notion called self-training, which is used quite extensively in the natural computer vision realm, as well as more recently NLP also. And the premise here is quite straightforward too. We start off with some limited amount of labeled training data. So in this case, we have 2 images and we know 2 labels for that. So we can train an initial CNN to be able to learn this classification. Now, once I only have these images, I'll have access to a new corpus of information where I don't have access to the label. So I'll only have the images. But in the first place, I've trained a teacher model based on the 2 labels that I know about. I can simply take that model and run inference on these new images that I've acquired. And I can build these pseudo-labels in the first place. And they're pseudo because we know that they might be noisy because they're all conditioned on the initial teacher model that has been trained. But now, instead of going from 2 images with labels, I've gone to 5 images with labels, even though the labels might not have the best quality. Then next, I can take this larger data set of 5 images with labels, and we can train a different neural network. It could be equal size, it could be larger, and there could be different methods to regularize it using some classical regularization methods. And now we train a new teacher model on those 5 images, and we can keep repeating this process over time. So we can either keep adding more and more data to infer new pseudo labels, or we can keep making our teacher model more and more expressive. And some of these self-training methods have achieved state-of-the-art performance even in a very limited data regime. So we wanted to see if this is something that we could use for some of our MR reconstruction problems. And just some terminology that we should be aware of here is that the teacher network is the initial network that has been trained to create the pseudo-labels. And the student network is something that learns using these pseudo-labels that have been created. And this can work in an iterative manner. So this was some work led by our PhD student, Belize, in electrical engineering, where we tried to utilize this for MR reconstruction. And the setting remains entirely similar. We start off with some images that are data pairs. We have some undersampled image as an input, and then we have the high quality version of that as an output. So this is what we use in our supervised learning problem. Then we can actually train an unrolled network to learn that transformation so that during inference time, when we get an image that's only undersampled, we don't have any sort of labels, we can simply run inference on our unrolled network with the teacher model that we've trained to create a pseudo-label image for this particular unlabeled image that we have. And now this creates a pseudo pair, and we can combine all the images that we have that are fully sampled as well as our pseudo-labels to train an additional student model to where we've artificially increased the size of our training data. So that's one approach that we use, where our teacher model was using scans from our unrolled network, but we could have a slightly different perspective. Within the same exact formulation, instead of using our unrolled network to come up with pseudo-labels, why don't we actually use some of our unsupervised methods that we know work quite well as the teacher model? So we can take this undersampled scan and we can still improve the image quality. So we're basically building better pseudo pairs here that we'll eventually be using in our downstream student model. So this really is trying to use the best information in a data limited manner for MR Recon. And the reason we decided to use the ConvDecoder in this self-training mechanism is because in a limited data regime, we can actually build better quality images using the ConvDecoder than our unrolled teacher. Here we see the zero-filled image, very poor image quality. There's a lot of artifacts that we can see through these lines. The unrolled teacher does okay in this limited data regime. I believe this was trained with 2 subjects only in a fully supervised manner. So we're in a very small data regime. And we see that it does a little bit better than these zero-filled images, but there's still some pretty problematic artifacts. However, our ConvDecoder can start with the same input image as a zero-filled image, but recover the signals a lot better. And this is in comparison to the ground truth image. So the premise behind the ConvDecoder here is we're using the best possible pseudo-label to be able to train this new self-training student-teacher model. And here are what some of these results look like. This, again, I believe is trained using only 2 examples in a supervised baseline. We have some ground truth image, and we have some model output for undersampled MR scans. And given that we're in such a low data regime, supervised baselines are not going to work because they still cannot recover too many of these artifacts. When we use a classical self-training approach where we use our teacher model that used an unrolled network, we see that the model outputs are a little bit better, but there's still some artifacts that are remnant here. But once we use this ConvDecoder approach to come up with weak labels for images, we see that we get the best possible reconstructions despite being in this very limited data regime. So the takeaway here from self-training was really that we kept our forward model identical. We knew exactly how the MR physics were working, but we simply modified how we're generating these pseudo-labels in the first place. And then second, we were able to condition these pseudo-labels on the structure of CNN structures in the first place, based on some of the insights that we had from the deep image prior paper and some of our initial observations about the ConvDecoder. But one of the questions that this led to is right now we're only modifying the pseudo-labels, but we're not necessarily using any domain knowledge that we have about the forward model. So this is what inspired us next to be able to build different semi-supervised methods where we can actually use what we know about MR physics to try to build a little bit more invariance into the model. So let me walk you through this network that we've built that we called noise to recon. And here we start off with our fully sampled case space in the same manner that we've done for all of our supervised examples. We can generate different undersampling masks to be able to simulate undersampled images. Now that we have this undersampled data, we can pass it through a reconstruction model and ask it to build some sort of image output. And we can compare this image output with the high quality target ground truth image that we've always been working with. And we can compute a supervised loss. So this is what we've been doing. This is what the standard supervised training pipeline looks like. But now we added an extra constraint to this where we can take this undersampled case space that we have, and we can actually add different sorts of artifacts to this. So in this case, we can add an additional level of noise onto these undersampled case space measurements. So now, instead of simply having the original case space, we have the model outputs as well as a noisy version of the model outputs. And if we want to be able to build a system that is invariant to noise, what we can simply do is we can force the model to make sure that the noisy and the non-noisy version of the images give you the exact same output. And that's where we're using this consistency constraint. And this is how we can actually improve performance of these models by using very limited training data once again. And this was again work led by two of our students in EE, where they're comparing these noise to recon methods. And you can see examples where only one subject was used for training, and we can get some very high quality images compared to the ground truth. And we can also compare this with a supervised only approach that used 14 times more data. And we see pretty identical image quality where we only used one subject and the baseline used 14. And if we just naively use the addition of noise as an augmentation, which is commonly done in a lot of classification type of problems, we add noise, we rotate, we flip, we saw that we didn't really see too much of a benefit in performance because we're not necessarily building invariance to that noise in our representation of the model because there is no consistency that we're enforcing. So in this manner, we were able to actually build up invariance to noise, which we know is a major source of artifact in MR images. So if one were to look at this from a high level, we've been able to build a generalized framework for enforcing consistency. The top pipeline here, once again, uses the supervised pipeline, where we have some fully sampled data, we have undersampled data, and we can build image outputs, and we can compare against what the reference ground truth images should look like. Simultaneously, we can have a completely separate consistency branch where we can work with undersampled data only that does not require any labels. And we have a full module to come up with realistic augmentations. And these augmentations is something that we want our model to be invariant to. And we can choose these augmentations to represent what we know about the forward model itself. So we can have physics-based augmentations where we've worked with noise and we've worked with motion. These are two of the biggest challenges that we face in clinical imaging. And we can combine this with image-based augmentation, such as rotation, shearing, and any sort of image or geometric transformations. And we also have worked on some curriculum learning about how do we actually schedule these augmentations in the best manner. If my network is just starting to learn reconstruction, for my first example, I don't want to expose it to a very challenging example. If we try to think about how humans learn in the first place, we want to start by learning simpler examples initially, and over time, increase the difficulty of these examples that are being seen. So that's exactly what we can do here using different scheduling methods. And using this entire consistency pipeline, we can actually be very robust to noise as well as motion artifacts. And here's an example image that we can see. On the left is some ground truth. And at inference time, we actually were able to simulate heavy amounts of noise to this particular image. And if we pass this image into a supervised network, which has never been trained with noise and motion artifacts, we see that the image quality is just terrible. If we saw the scan, we would absolutely request a rescan for this, and we'd have to call the patient back. However, our proposed method, Vortex, which we've been able to regularize using motion as well as noise augmentations, performs quite well. It is a little bit blurrier than the original ground truth. However, when we compare it to some of these supervised baselines that are entirely off base, we can still maintain adequate image quality. And depending on what sort of diagnoses one might be interested in, one can still evaluate what the clinical question is. But now this leads to another question about how do we actually evaluate the image quality? We always have to think of different use cases, Some use cases might require high resolution, some use cases might require slightly lower resolution. And what we found is fundamentally, there's a bit of a discordance between the quantitative image quality metrics as well as the qualitative image quality metrics. And let me show some examples that depict this. On the left is some ground truth image, and the three different panels that we see here are networks that have been trained with different reconstruction losses. So we're enforcing an L1 loss, an L2 loss, and an adversarial loss. And interestingly enough, if you ask me, or if you ask quite a few radiologists, they might say that the best image out of these three losses is this adversarial image, because it still has this high frequency information. It has a little bit of noise, which actually adds to the texture of images that one is used to seeing. And most folks, I think, would say that these adversarial images compare the best with these ground truth images. So that's our qualitative perception of image quality. At the same time, though, if we actually look at some of the quantitative metrics that we use to evaluate these algorithms and to actually train them in the first place, we see that these adversarial images have the worst of all three quantitative metrics. So there's a fundamental discordance. And when we try to optimize for one metric blindly, it might actually end up resulting in worse images than what one would want in the first place. So in order to address this problem, we've released the SCIMkey dataset that we call the Stanford knee MRI with multi-task evaluation. And for the first time, this dataset includes not just the raw data that we need to solve the reconstruction problem. Simultaneously, we actually have clinically relevant metrics also. So in addition to just stopping at this reconstructed image, working from the case space, we actually have dense labels about tissue segmentation. We have dense labels about pathology detection, where we have bounding boxes for around all the abnormalities that we care about. So really what this can enable us is it will provide an opportunity to move away from these metrics that we know are not very useful to evaluate qualitative perceptual quality. And instead, we can now just start using this data set to be able to optimize for metrics that we know have a clinical significance. So we know that tissue segmentation is important because the volume of different tissues changes when one has arthritis. We know that these pathology bounding boxes are important because that is what is evaluated clinically. So this could be used as a clinical decision support system. So once again, the message here really is we don't have to rely on some of these imperfect metrics that we know of already. Instead, we can simply solve for the clinical metrics, because at the end of the day, one could argue that generating a medical image is useless in and of itself. What is useful is what are some of the insights that you can draw from that image? What sort of clinical actions can you take based on that image? And hopefully this data set will allow us to do this, because now not only can we experiment with different reconstruction algorithms, but we can really see what their impact is on downstream image analysis too, which is why the data was acquired in the first place. And maybe very quickly, I'll mention some of these slides in examples or in scenarios where we don't have the ability to densely label data, where we don't have the ability to segment out different tissues or to be able to build these bounding boxes. We're actually using some improvements in self-supervised learning to build good extractors of image quality. So we can do something quite straightforward as a pretext task. We can take an original image and we can corrupt it. So this is very similar to what masking does in NLP. We simply mask different parts of this image and we build a neural network to predict what should be in those boxes. And once we do this, we can actually use this neural network as a feature extractor so that when we're actually computing losses of our reconstruction model, we feed in our ground truth image, we feed in the test image that we're working with, and we take this pre-trained self-supervised network. And instead of trying to optimize for peak signal to noise ratio or structural similarity, which are metrics that humans have derived, can we actually move away from that? And instead of learning about how humans visualize these images, why don't we actually use how machines interpret these images in the first place? So instead of trying to optimize for the L1 or L2 norm, we're simply trying to optimize for the features that have been extracted using our self-supervised network. And here's some examples about why this might be beneficial. On the x-axis here, we're seeing structural similarity. And on the y-axis, we're seeing one of the metrics that we've created using our self-supervised feature distance. And I just wanted to compare two examples that have been picked out here that have near identical structural similarity. So if we actually use that as a metric, both of these examples would probably have passed with flying colors because having an SSIM of 0.9 is quite high generally in the computer vision community. However, once we actually visualize these images, we'll see that this image in blue, even though it has a high SSIM of 0.92, there's a whole host of image artifacts that have not been resolved. If we show this to a radiologist, they probably would not be confident about rendering a diagnostic verdict. So even though the metrics here are high, with traditional methods, our methods actually show that this is an outlier and most likely should not pass our quality control step. And here, this is another example where the structural similarity is quite high, 0.88, but even our self-supervised feature distance metric shows that the metrics are within reason, and one can see that the image quality here is quite high. There's no obvious artifacts. So really, the goal of this self-supervised feature estimator is to be able to be used as an optimization method so that we can directly optimize for what our networks think is important, and as a quality control tool so that once we're actually deploying some of these methods in the clinic, can we have some sort of assurance about how well they work? And we just wanted to compare against some traditional perceptual losses that people use quite often, even in medical imaging. Typically, perceptual loss is computed using the VGG network that was trained on ImageNet, and the distribution of ImageNet is very different than the distribution of medical images. So our method still outperforms these VGG-based perceptual losses. So really, the overall takeaway, hopefully, from some of these experiments is that if we add domain knowledge into our problems, we can reduce the need for data. And this could exist in multiple different workflows. We can build novel unsupervised, semi-supervised settings where we can really take insights about what we know about the physics, as well as what we know about the ML systems that we're working with. And I think being able to work on clinically relevant metrics, as opposed to simple heuristics that we've come up in computer vision, can really drive implementation of these new methods. And to be able to do this, we tried to open source all of our data and all of our source code. So within the next week or so, we'll be releasing the SCIMT dataset, which was our multitasking dataset. We'll have all associated source code also released, where people can test out their newest reconstruction models, their newest segmentation models, their detection models, and really enable a new line of multitasking research. And we also have other medical imaging analysis software that we've open sourced that can really help with a lot of these downstream tasks, such as segmentation, image registration, quantitative fitting. So we really want our tools to be able to benefit the community at large. So as conclusion for this talk, hopefully I've shown you that there's a lot of excitement within the upstream AI field in radiology too, where we can use machine learning to improve image quality. And really the best way forward is by combining what we know about the underlying system, about the underlying physics, with some of the data-driven benefits that we can get with most ML models. And really the hope of creating and sharing these data sets and coming up with metrics is to be able to build bridges between the machine learning as well as the medical imaging community, because I think by coming together, will we be able to drive the most change going forward. And I would like to acknowledge a whole host of folks who have made this work possible. Highlighted in bold are all the students who've contributed data, who've actually built out everything that I described here. So a huge thank you to all of them, some collaborators, as well as funding sources. And maybe just wanted to make a quick plug. There is a new PhD program at Stanford University that's starting, and this is actually the first PhD program offered in the School of Medicine. So if you're interested in biomedical physics, where we learn about physics of different medical imaging modalities, how we can use machine learning to advance some of these, please consider applying. There's a lot of information online. And with that, I'm happy to take any questions.
Well, thank you, Akshay, for that fantastic presentation. It's so nice to hear the innovative ways in which we need to devise new methods to address some of the use cases in medical imaging that can be very different from just conventional computer vision. So thank you for that. There have been a lot of questions coming in, which is fantastic. And I'd say a lot of them focus on the notion of hallucination and how we handle rare diseases and evaluation metrics. So I'll maybe take you through, I know you covered some of these, particularly near the end of your talk, but I want to maybe take you through some in more detail. So Luzuko, Daixing, and Ravi asked about this notion of how do we know that we're still able to capture abnormalities that might be rare, or that we're not distorting pathology with some of these methods that are creating higher resolution images?
Yeah, those are really good questions. And these are some of the questions that keep me up at night too in a lot of this research. And I think there's a couple of different perspectives that one could take to address those questions. One could be from the model perspective itself. So as I described, some of the unrolled models that we're building have inbuilt data consistency blocks in them, so that whenever we're outputting an image, we're actually making sure that it is consistent with some of the undersampled data that we've acquired in the first place. And because of that consistency, and because we know how the Fourier transform works, it would be highly unlikely that a tumor pops up that spans multiple different pixels that didn't exist in the first place. So within our optimization process, by enforcing that consistency, we can actually mitigate hallucinations. So that's something that we can do from the model perspective. But I think from the second perspective is we just need better evaluation metrics. Things like peak signal to noise ratio will distort a lot of these images. It will lead to blurrier images. If there are artifacts, it will really cover those. So I think moving away from these traditional reconstruction metrics and really trying to optimize for what do you care about downstream? Why are you acquiring those images in the first place is probably the best way in which we can address some of these problems. And that was really the motivation for the new data set that we've released. Instead of just trying to optimize for peak signal to noise ratio, why don't we make sure that my new reconstruction methods has the same sort of ability to segment tissues with the same volume and with the same characteristics? Or my new reconstruction method might be able to build the best classification system. So I think there's some modeling approaches as well as some evaluation metrics that could be helpful there.
Great. And a related question about robustness that, again, kind of relates to this hallucination question. So how do you think about the robustness of these acceleration methods, and how can you be sure that your decoder block is not creating new features?
Yeah, that's a really good question. And I think there have been a few papers that have come out over the last couple of years that have questioned the robustness of deep learning-based methods specifically. And although I didn't necessarily have the time to get into this in our talk today, we recently had a publication at ICML where we really systematically tried to evaluate how different image reconstructions methods perform in response to adversarial noise. So what we actually found out is that all image reconstruction methods, the ones that use deep learning, and even the conventional ones that we use in the clinic, such as compressed sensing, can all be susceptible to these perturbations. And it's not something that's only specific to these deep learning models. So I think that observation was really insightful in just making sure that we're not discrediting deep learning-based methods without a fair comparison. So that was the first takeaway that we had. And then I think the second takeaway that we have is because we know what sort of artifacts one might expect in terms of robustness. So we know the reason a lot of MR exams are not robust is because of artifacts like noise and because of artifacts like motion. Even if we don't have a supervised training data set that has those artifacts, using our knowledge of physics, we can simulate those. And that's exactly what we did with our semi-supervised consistency platform. And we can start simulating more and more of these artifacts so that our network is implicitly invariant to those robustness issues at inference time. Obviously, we've only just started that work, and I think there's a lot that can be done. But once again, I think it really comes down to taking what we know about simulations and about the physics and baking that into a model to try to make our model robust to changes we expect to see downstream.
Great, thank you. And then there are a couple of questions that came in about the data set. So Miriam asked, how did you construct the ground truth? And others were asking about exactly what tissues and pathologies are represented in the SCIMT data set.
Yeah, I didn't have too much time to dig into the specifics, but in terms of some of the constructions, this data set was acquired at Stanford Hospital. These are patients who came in for conventional knee MR scans, and we had a process where if they offered informed consent, we added an additional research sequence where we're able to acquire fully sampled data. We only undersampled that data by a factor of twofold, but we're still able to build high quality reference images. So this is a clinical population with a lot of different abnormalities that we'll be seeing. And we have the case space for that. We have the reconstructed images. And in terms of some of the outputs, we have tissue segmentations for articular cartilage, which is a tissue that's commonly affected in knee injuries and in knee osteoarthritis. And we have bounding boxes for any sort of abnormalities in the cartilage, the meniscus, and the ligaments. All of the tissues that a musculoskeletal radiologist would evaluate routinely anyway. So we have these dense 3D bounding boxes for all of those. And in addition to this data set also allows us to work with quantitative MRI metrics. Typically, an MR image is qualitative. One would just say this pixel is slightly darker than the pixel next to it. Using this imaging method, we're actually able to acquire some quantitative information about metrics that correspond directly to the biochemical status of the tissue. So we have the images, we have the quantitative parameter maps, we have the segmentations and the detection labels. So hopefully it could be of good use to the community.
Wonderful, thank you. You'd mentioned early in your talk about decision support as a typical role for AI, and we do see a lot of that. But when we build those kinds of models, there's often a human in the loop as kind of a backup. So if the AI algorithm might identify something as a nodule that's not really a nodule, the human radiologist can look at that and say, I'm just going to ignore that marker.
Yeah.
In the case of reconstruction, sometimes that data may not be even sampled in the first place. So how do you handle that? And are you planning to use more human-based evaluation of these results?
Yeah, that's a really good question too. And I think the answer there revolves around some of the constraints that we've talked about already, revolving around data consistency. Can we be sure that what our model is outputting is realistic? In the ICML paper that I described, we actually were able to build up a smaller data set of adversarial examples that for some reason just had worse performance than others. And we're actually investigating different ways in which we can a priori predict what the performance of my reconstruction algorithm would be. And we envision this to be working in real time on the scanner. So let's say if my clinical protocol requires 4-fold undersampling, but my quality control system now says, hey, with 4-fold undersampling, I predict that the images will be pretty bad. So while the patient's in the MR scanner itself, why not just acquire a few more data points and push down on the acceleration to be sure, because we've been able to build that predictive algorithm in the first place. And there's actually fundamental differences in the adversarial examples that we noticed and the normal examples in how the energy is distributed in case space. The adversarial examples have more high frequency content, which makes sense because if we skip subtle details, we'll never be able to reconstruct them in the first place. So I think there's a lot of things that one could do upfront in trying to predict some of these features and to account for that in real time within the scanner so that before the patient goes home, we can still get the right data that we need.
Mm-hmm. Great. Well, I see we're at the top of the hour, and I just want to thank you, Akshay, for joining us today, and thank the audience for all of their great questions. Just an administrative item, there will not be a research seminar next week because HI will be hosting their fall conference, 4 Radical Proposals for a Better Society. Some interesting proposals there. Check it out. The conference is open to the public virtually, so you just need to register through the HI website. We hope to see you all there. Thank you and good afternoon.
Thank you, Kurt, and thank you, HI.